continuing from this. Hello. It's on. Is it on? Yes. Cool. All right, let's get started. So today I'll tell you about gradient descent. And the random decision I made, which was also influenced by further dissatisfaction with now both of my lectures yesterday, was I'm going to spend most of the time today on the convex case, actually. But if you're an expert in the convex case, then I urge you to guess what I'm going to show. I'll try to have something new even for the people that are experts in the convex case. And the reason I'm presenting the convex case is because, first of all, basically everything we did in deep learning theory with optimization is not helping us with analysis of transformers. So that's issue number one. Issue number two is, as I'll explain, it turns out enough things are open in the convex case that solving them might help us with the non-convex case. Okay, so let me give you a bit of brief background before I tell you how we'll divide up the lecture today. So just a reminder, and I know you did some of this in the other lectures, but for the most part, I'll talk about gradient descent, which is in discrete time. A few times I will discuss what's called the gradient flow. I have very serious mixed feelings about presenting the gradient flow. For those of you that aren't familiar with it, you can kind of consider it as an infinitesimal step size gradient descent. So if I just rewrite the sides, then I get this. So you can see how this sort of looks like a finite difference equation that in the limit can maybe kind of look like this if you squint. Oh, in this notation. So I mean ddt of w. So yeah, I'll mainly talk about that, and I'll talk about some of their differences briefly. Yeah. So what we'll talk about today is as follows. So the first section I'll tell you about is what I will call norm bias and path following. So a natural question that people, especially with an optimization background, encounter when they run into machine learning is, why do we use these first order methods, which if you went back 3 decades in optimization, that was kind of what you learned on day one, and then you discarded and you talked about fancy solvers. No one in machine learning uses any of the fancy solvers. And it's very important to reflect on that. And there are a bunch of reasons for it, but one of the reasons is that gradient descent doesn't just minimize an objective. That's kind of the last thing it's trying to do. It actually follows a very specific path to minimize the objective. And this seems to influence the statistical properties. So that's the perspective I'll take. So this will be in the convex case. And this is fairly open, actually. So it's not well understood. And then what I'll tell you about is briefly, I'll tell you about some MLP cases. So I'll tell you how part of the story interrelates with what I tell you in part A. Okay? All right. So now that I said that, let me give some remarks about the setup and some things we will and won't discuss. And then I'll see if there are any questions. Also, you should feel free to say, why aren't you presenting my favorite result by my favorite so-and-so? And yeah, I'm sure that's a good result, and I'm happy to give comments on whatever paper you think I should have presented. So the first thing to remark on, as I was saying, is why first order? So there are a couple lazy reasons that people like to give. One, of course, is that it has cheap per iteration complexity. And the other, of course, thing that goes along with this is especially with stochastic gradients. So first order methods interact extremely nicely with stochastic gradients. And yeah, so that basically, to a great extent, settles them. And so fast methods, so something like a Newton solver, which have a bad iteration complexity, still suffer statistical error. So let's say you use a lot of big brains and you run some log 1 over epsilon or log 1 over epsilon type solver or something. It turns out that it's still paying a 1 over n or 1 over statistical error. So all of those logs and exponential rates didn't actually mean anything once you run into the statistical error. And then, so the other comment is one that I'm going to talk about here, which is it follows a good path. So not only do we not run optimization methods to convergence, not only do we stop them early, there's a lot of evidence we stop them early at a point that is uncorrelated with where they're going. I don't just mean slightly different, I mean uncorrelated with where they're going, nearly orthogonal. And you can prove this in many cases, and it's not well understood. So a limiting theorem about a gradient method, it's not clear that it has any relationship to the gradient methods people use. I'll also say that there is the hardware lottery reason that they win. So there's a lot of perspectives on why deep learning is the way it is. And one is this hardware lottery. You can Google this. This is a paper somebody wrote. I think her name was Sarah Booker or something. I forget the exact name. But anyway, this perspective is basically that there's this kind of evolving and self-reinforcing hardware and software loop going on. And so if one of you come up with something better than a transformer or something better than Atom, you have to contend with the fact that NVIDIA engineers and NVIDIA driver writers, they're checking that Atom works well. They're checking that DeepSeek runs well and things like this when they roll out new driver updates. That's who you're fighting against when you come out with a new architecture. It might be better according to some mystical machine on another planet, but you have to fight with the coevolution of all these things. And the reality is that all of the methods that we're using, they've been co-evolved with first order methods. So transformers, if we didn't use first order methods, might not be the best thing, but we use first order methods. Okay, so that's, I mean, this is kind of an annoying point, but it's something you have to contend with if you try to come up with something better. Okay, any questions about these points? Okay, another remark I want to make is aspects of this I'm not discussing today, so aspects of the setup. So one thing I won't talk about is the effect of batch size and stochasticity. I will basically ignore that. I will show you a few times, for instance, I'll prove a theorem and then I'll write out the corollary if you have stochastic gradients, but I won't tell you anything about them. I mean, I'll tell you how to prove it, but I won't really discuss it. I also won't talk about large step size. Because in practice, these interact closely with batch size and many other things. I'll say and generalization. Okay, so there's just a lot going on here. And this is one of many reasons why I'm not so comfortable reasoning about gradient flow, because gradient descent actually can be quite different. Okay, so any questions This is basically the end of my preamble, and then I'll prove some stuff. Okay, cool. Right. Okay, so let me do this item A. So in the convex case, and let me just say that I'm only going to use convexity. I'm only going to use one definition of convexity. And I'm just going to loosely write down gradients today. I won't talk about generalizations, but you're fine to ask me about things like how to do gradient flow on the ReLU and stuff if you care. So the only definition of convexity I'm going to use is the so-called first order definition, which is that you're always lower bounded by tangents, which of course is the definition that carries through if you're convex but not differentiable. So if this is some point W, and I'm looking at some other point W prime, then I'm comparing the function values of W prime to the function values of this lower bounding hyperplane. And this lower bounding hyperplane is exactly given by this equation V maps to, so this is, I'm just writing the equation of the lower bounding hyperplane. Nothing fancy. Sorry, too many W's. Let me put U here. Okay, V maps to, okay, I messed up my notation. Excellent. Okay. Okay. So convexity is just that you lie above all of these lower bounding hyperplanes. Okay, and that's just the equation for the lower bounding hyperplane. Oh, thanks a lot. My bad. Yeah, sorry, I don't know why I like swapped all of them 10 times. Okay, so this is the only definition of convexity I'll use. And yeah, actually, since this is a summer school, let me just make two remarks. If non-differentiable, you'll use instead something called the subgradient, and it is the set of slopes which satisfy this definition. So instead of making this a characterization, just make it a definition. So it's the set of lower bounding hyperplanes. And a function, all convex functions are, they're a convex function over R to the D, this set is always non-empty. And I'll also just make a technical remark for people that were curious since I referred to it. If not convex, there is a standard notion of a differential. It's something called the Clark differential. The Clark differential, it agrees with the subdifferential for convex functions, but it's always non-empty for locally Lipschitz functions. So if you ever read a paper that has gradient flow on a non-differentiable function, the right way to do it is to use the Clark differential. I have to say this is a point of embarrassment for me. I know a lot about the Clark differential. I learned about it because I thought the ReLU was here to stay. Whoops. Like serious oops. And not only that, PyTorch never correctly computed the Clark differential. It computed something else. And if you adjust PyTorch to correctly compute the Clark differential, it just makes things run slower. So I'm just giving another cautionary tale of learning a lot of mathematics. Okay, so that's convex. And to motivate this, I'm going to tell you my dream theorem of what I wish I could prove in a lot of cases for gradient descent. And that's in the case of least squares. Okay, so for least squares, without knowing anything, just knowing basically what a matrix is. You don't even need to know what a gradient is technically. You can write down an exact characterization of the path followed by least squares. So let me write this down for you. And I should say that almost everything I do today is going to be for not least squares, but for the cross entropy loss. That upsets you, I can explain. They are very different. Okay, so I'll use this loss. And I'm going to let W bar be any optimum. So that would just mean it has to satisfy this equation. If you know about first order conditions, this is just taking the gradient and setting to 0. But this is also something called the normal equations, which you can just motivate directly from least squares without knowing about convexity. And I'm also going to use the SVD of the data matrix. Okay, so I'm just setting up the notation. Okay, and here's what you can show. So then if I run gradient descent, so that equation I wrote up there with this, with the gradient of this objective, then I get the following. If I look at Wt minus W bar, okay, so this is any optimum. This is my iterate at time t. And I'm not going to look at the norm of it or something like that. I'm going to look at something much more refined. I'm going to look at it in the direction of the right singular vectors. Okay, I'm going to characterize what it does in all of the right singular vectors. And I'm going to write it down with equality. Okay, so I'm going to get an exact characterization of what the gradient of descent and flow are doing. And what you get is very clean. You get exactly this. Okay, so let's interpret this for a moment. And the proof will be very short. I just want to interpret it first. But again, for me, this is the dream. This is something I wish I could prove in a more general setting, like something like it. When I say I want to prove this, I don't mean singular vectors, but something like it, a characterization of the path. So let me give a first interpretation. So if this is what the covariance of the data looks like, okay, so I'm drawing sort of the first ellipse of the distribution of the, so this is the, so here's the first eigenvector. I mean, here's the first eigenvector direction, here's the second eigenvector direction, okay? So, and let's say the optimum is W bar is over here. It says that gradient descent is going to follow a path like this. And if I change the distribution of x and I leave W bar in the same location, then it's going to follow this path. Okay? And the point is, when you run gradient descent, you don't stop it here. You stop it here or here. You'll get a totally different solution. Okay? That's straight from the equation. Oh, I left out a, sorry about that. I left something out. So because the contraction is x, so you have this exponential contraction, and the coefficient is given by the Singer values. By the way, I know that I'm cartooning it on the board, but if you just code this up, it's the first time I coded up, I was actually shocked. I thought the picture was just in my head, and it was much more extreme when I ran it. Okay. I should also say that this equality is funny because normally you're supposed to take eta to be smaller than something. This allows you to make eta large, in which case it diverges. Of course, to make the equation work out, you're going to want to make eta balance with the Singer values, of course. Okay, so that's one interpretation. Yeah, another interpretation is that, So if W bar is actually the ordinary least squares solution, so the ordinary least squares solution is I invert all of the, I take the pseudo inverse of the labels. Okay, so if it's this, then and W0 is in the span of V1 through VR. So if this W0 is in this span, then this thing implies that WT goes to the WOLS, ordinary least squares solution. Okay, but it gives a very explicit way to write this down. You can also just linear algebra this claim, but this you can read it off of this. If it also tells you that if I have a component at initialization which is not in the span of the data, then I'll never clear it. Okay. Yeah, and at least one person in the room has seen me do this before, but this is pretty cool. Okay. So I'll make one more remark, which is that I remember when I was a PhD student, when I was reading a lot of papers about least squares on sparse problems and different types of problems, there were a lot of algorithms that had to do spectral filtering. And what this is telling you is that the gradient descent will just do spectral filtering immediately. So if you stop it early, it's just ignoring the small eigenvalue directions. So GD automatically spectral filtering. And why does this matter? Well, it matters because sometimes they might be very statistically unstable. You don't actually want to learn them. You want to stop early. Okay. So any questions about this interpretation or where we're going with this?
Can you explain again what is spectral filtering?
Oh, I just mean that I'll write it down on the board later, but I just mean that so this is the solution we would asymptotically converge to, but I also made a big deal saying that you never run gradient descent to convergence. And what this path is saying is that what you're actually going to be close to early on is if you just truncate the summation and just do the first couple terms. Yeah. Just threshold the spectrum on the noisy ones, pretty much. Yeah, actually, from the lecture yesterday, we know that it's really hard to estimate those low eigenvalues anyway. Yeah, what's the question?
Okay, so like you mentioned, interpretations, why is the WT will follow the junction of the largest negative values and negative vectors. Second is like if you say the initial condition displays in the span of all the vectors that the thing will converge. Like is there any like for the first interpretation says it may not converge, but it will add seeing.
No, it converges. No, it converges. Yeah, no, okay, so if you initialize in the span, first of all, you will converge to the ordinary least squares solution. And if you're not in the span, you're going to converge to the ordinary least squares solution plus your component that was orthogonal to the span with equality. Yeah. It's also interesting because it actually gets very mind-boggling once you start really thinking through what's going on under the hood, because you look at this and you say, wait, so should I never run ordinary least squares because gradient descent on least squares actually solves ordinary least squares? But then it finds the minimum norm solution. I mean, this is another way to characterize this as a minimum norm solution. But then you remember that ordinary least squares internally is implemented using an iterative solver anyway. So it gets a little bit confusing, but yeah. Anyway, so yeah, it converges to a minimum norm solution or this ordinary least squares solution plus the component orthogonal to it that it started with that never gets cleared. Yeah? Wait, what?
Are you referring to the curve down or some more general?
This is like, I'll show you how to prove this. What I would like, so this is a tight characterization of the path followed by gradient descent. I'd like to prove this in generality.
So where by generality you mean for other functionals rather than just
Change everything and yeah, change everything in the problem. Yeah, yeah. I'll explain why I care about this so much. Yeah, to be clear, uh, if you don't mind asking that question again later, it'll be better. Okay. So speaking of which, let's just do the proof right now. So um, yeah, so the to do the proof, there's a few ways to write it, and I'm going to write it one way, which I don't know if it's the nicest way to write it. So I'm going to not introduce the VIs. So just to make it simpler, I'm going to say fix. I'm going to fix some um, W s minus 1 and W prime is equal to WS, which is WS minus 1, minus eta grad L W, which is WS minus 1, or just W minus, and then we can fill in the definition. So X transpose XW minus Y. Okay. So in other words, I'm fixing some iteration. I'm fixing an iteration X, sorry, an iteration S. I'm just making W be the previous iterate, W prime be this iterate. And that way I don't have to write a bunch of subscripts when I write this. Okay, so let's just look at what is the central object in this theorem. Wait, is the whole theorem visible? Okay, good. Okay. All right, and there's really, if you want to write an equality, there's really nothing you can do except expand a bunch of definitions. So I can expand out the gradient of ourselves, but because this by choice has this equal to 0, I can also add that in. Okay. And again, for those of you that like doing it yourselves, I urge you to just finish the proof while I'm talking because we only really have one choice at every step of this. So, okay, let's expand the definitions here. So I get eta and then 1 over n xt xw minus y. And then I'm going to get the same for w bar. So xt x w bar minus y. And nicely, these will cancel. So I have w minus w bar minus eta, then, sorry, eta over n. Let me just write a little differently. Eta over n, x transpose x, w minus w bar, which is the same as, now let me pull this entire term through. So I have identity minus eta over n, and let me expand what this is. So if I take the SVD and I multiply it by its transpose, I get this quantity, and then w minus w bar. Okay? So let me just say what steps I did once again. So I wrote out the definition of gradient descent and the fact that this one has 0 gradient. Then I just expanded the form of the gradient update. And this is why you don't need, I said you don't even need gradient descent for this. You can just treat this as an updating algorithm and not interpret what it means. Then I collected terms, and then I pulled terms through to the front and definition of the SVD. And we're done because if I just left multiply by VJ transpose for some fixed VJ, it'll pass right through this thing and it'll kill off all the terms that are for the other singular vectors. Okay? Okay. Any questions? All right, so now what I'm going to show you is the closest I can get for convex functions. And the answer is not very close, but I can try. Okay. Okay. Okay, so now we're going to consider the convex and smooth case. Here I'm using this definition smooth, which is used in the machine learning literature. So this does not mean C infinity, which is what smooth means for math. What smooth here means is one of two definitions. People either say it means that the gradients are Lipschitz, which means this. And as a consequence of this is what some people use as the definition, which is that I can upper bound myself with the second order Taylor expansion. Formally, this actually gives something stronger. It gives a two-sided version of this inequality, but we don't need that. So this is the version we will use. Okay. And let me just point out that, let me just make a remark on why we are making these assumptions. So why these assumptions? Because you might say that in whatever deep networks, neither of these are true. So even if you use a smooth activation, if you look at this is trivially false everywhere except a small subset of the domain for something like a transformer or multi-layer network, because when you take the gradient with respect to one layer, by chain rule, it kicks out all the other layers. So you get something which is highly non-smooth. It just has highly non-smooth in the sense that the Hessian just has all these extra terms that are multiplied together. So it has very fast growth. But both empirically, so let me write this down formally. So many, or I would say even most deep learning optimization proofs use these ingredients. They're sort of a good ladder to build up off of. Okay. And let me also make one more comment about convexity. So I already gave you the definition of convexity, but standard training now uses the cross entropy loss. And the form of the cross entropy loss, I won't use the form of the cross entropy loss. But I just want to write it down at least once. Okay, so what this is it's for the true, I have my multi-dimensional output. I take the negation of its prediction on the correct label plus the log sum exp of the other ones. And this is the same as log 1 over the probability under the model where the model is doing softmax prediction probabilities. I have to tell you that I don't understand why this is basically the only function in mathematics. The side comment, I run into log sum x basically everywhere in mathematics. I've never not run into it, right? Like how do you prove Chernoff bounds? You look at the log MGF, that's log sum exp. There's like nothing but log sum exp in math, and I don't understand why. Like I don't understand why we talk about functions. We should just talk about log sum exp and not teach anything else. But yeah, basically nowadays this is almost everything in the LM pipeline. So the pre-training does cross entropy loss. If you remember, you have this input sequence and you generated logits or the outputs. So that's pre-training uses this. Post-training uses this. DPO uses this. The list goes on. Now people are even using this for image generation and not diffusion models. So yeah, it's cross-entropy everywhere. So just side rant. I don't understand how this happened, but it's happening. Okay. So now let me tell you a consequence of smoothness, and then I will tell you the theorem. I think people call the descent lemma or the descent condition. So if I just invoke smoothness one step, so if I just take that definition I wrote right there, this second line, and I plug in gradient descent, then I'm just going to grind the definition. So now I would have next iterate minus previous iterate. So the W's cancel, and I just end up with A to FW. And same for the difference term. So I have a norm squared with A to FW inside of it. So if I collect terms, because this is norm squared, this is norm squared, then I get minus A to 1 minus A to beta over 2 times this. Okay, and moreover, so most people then say, okay, it's natural to assume that eta is less than or equal to 1 over beta, in which case you get a further inequality, which is this. Okay. I want to make a few remarks. I want to make a few remarks about this. So first, so the descent lemma is fault for stochastic gradients. You take stochastic gradients, your expected loss or your population loss is not necessarily monotone decreasing. So we'll see analogous lemma with stochastic gradients, but on the expected loss. But this is actually a lame excuse. It is also the case that even if we do full batch gradient, often in machine learning, we don't have a descent lemma. We use large step sizes. So I'll just say this goes back to the other comment I made, which is I don't want to talk about large step sizes today, but I'll just say that large step regime without descent still important / interesting, just out of scope. There just isn't much research on it. Okay. So here's the best. So now I'll show you the best I can prove. Okay, I didn't expect things to work out nicely because obviously I'm just winging it, but I will be able to put both theorems next to each other. So now if I have F is convex and smooth, okay, this iterate sequence is given by, let me say beta smooth. So I'm using this small step size. Okay, then for all W bar and for all T, let me just explain what W bar is here. So for this theorem, I needed W bar to be in this subspace of solutions. Over here, I'm going to let W bar just be anything. So you can plug in garbage if you wish. You can plug in the truncated SVD solution. You can do whatever you want. And F is just convex here. So I'll say the theorem in two ways. So one way, so you might argue that this is what you want But in machine learning, it doesn't matter if you minimize the objective. If you want to minimize the objective, just memorize your training set and go home. We also need the predictor to have low complexity. So that is what we get from this theorem. So if you've seen this before, you've probably seen it with just the term on the right-hand side, but I've never understood why people removed the left-hand side, because this is what you need to do machine learning. Okay. So let me make this more emphatic. I'll say in particular, we have the following dichotomy. So either FWT is less than FW bar, or the norm of WT minus W0 is less than or equal to 2 times the norm of W bar minus W0. Okay? Let me actually not comment on this first one, which you might just say looks like something you've seen before or looks like whatever. Let me look at the second one. So one way to interpret the second one is you run gradient descent until you're near your comparator in terms of function value, and then you know that you're also just 2 times in terms of norm. So what this is saying is that gradient descent is very nicely trading off between both the objective value and the norm. And for those of you that are familiar with how statistical bounds work, just being 2 times a factor off optimal is usually enough to get a very good statistical error. Okay, so any questions about this? Either if you have seen something related or have not? Let me give some remarks about this. Sorry. So either our function value is small, or our norm is 2 times the norm of the comparator norm. So this is WT minus W0 less than or equal to W bar minus W0. So if you want, just set W0 equal to 0, then it's WT is less than or equal to 2 times W bar. Yeah, yeah. Yeah, sure. So, okay, so most statistical error bounds scale with norm of WT. And this is saying that gradient descent is just going to maintain that it's 2 times the optimal thing for any W bar. So if you choose W bar to be a truncated solution, a regularized solution, it'll be for that. So let me just give an example. So e.g., so define W lambda is equal to the analog of the ridge solution for this problem. Then, and pick, so pick WT such that you can do this. Sorry, let me make it this way. Okay. This is WT plus 1. This is WT. This is W bar. Picks up. Then we have that FWT is approximately, this was supposed to be lambda, FW lambda, and F, and the norm is similar. Okay, so why does this matter? It matters because, so let's say you know a problem is ill-conditioned and you want to use a ridge solution. What are you supposed to do? Are you supposed to solve ridge for a billion different ridge choices? Are you supposed to have nature somehow tell you what the optimal lambda is or what the optimal, what the optimal norm is? No, you don't have to do any of those things. You just run gradient descent. Yeah.
So is this the same as the more textbook ones about like if it's convex and Lipschitz and all that?
There is a relationship, yeah. So the proof is very similar, but the main thing is that this term is not dropped. So if you look at those proofs, they essentially always drop this term.
And I'm sorry, but what exactly is W bar? Is it the optimal solution?
Often the optimal solution is bad. So it's better to plug in something else like W lambda, this ridge solution. So yeah,
The optimal solution bad.
It can be bad for a statistical problem where the optimal solution for the training error overfits and is just a bunch of noise. So I can actually tell you that just right now. Let me just do that right now because I can tell people are unhappy. So there's a paper. I am one of the authors, so take it with a grain of salt. I think it's from this year. So I'll say for a certain high dimensional cross entropy problem. Okay, and so when I say for a certain cross entropy problem, I mean that for certain high dimensional is one of these things where you have to choose like the ratio between n and d and all these things in a certain way. But it's a high dimensional problem in the case in the sense that n is larger than n is smaller than d. D is significantly larger than n. So for a certain cross entropy problem, we have the property that the gradient path goes like this. If you stop very late, then you get a bad cross entropy and misclassification error. So this is what I was saying about the final solution being uncorrelated. So both the cross entropy error and just the 0, 1, the probability of making a mistake, are bad if you run for a long time. You have to stop early, and the estimator is exactly this one. So you choose WT such that you sandwich a good solution, which you can find by cross-validation. This one has good CE and 0, 1. And this one is also bad, just W0 and W1 are bad. So gradient descent follows a path, and you have to stop here. You can't run to the end. And I guess going back to the question, why is optimum bad? It's because you don't care about the optimum of the training error. You care about the optimum of the test error. And you're using the training set as a proxy. Okay.
On the left-hand side, you have like WT minus W0. So like that's just saying that WT is not so far.
Less than equal to 2 times W bar minus W0. So whatever distance that the comparator or the semi-optimum would have to travel, you have to travel at most 2 times as much. No, you shouldn't look at it as far from the starting point. You should compare it to how far the optimum traveled. I feel like we're talking past each other since you just repeated yourself twice. Maybe say it in a different way.
Yeah. Like if t equals 0,
Mm-hmm.
like if you just stop at your initial solution,
Mm-hmm.
that holds.
Right?
And then you were saying in particular, either something is true or something else is.
Okay. So the way to interpret, okay, now I understand. Okay, the way to interpret this is that until this condition holds, this condition holds. So the best way to interpret this is the way I did it over there. So just run until one step after the point that this holds. So you look at the first step where this inequality is violated. You know that in the previous iteration this held. So you know that in the first condition, you know that in the first iteration where this holds, your norm is basically satisfying this too. So this almost says that there exists a point which satisfies both simultaneously. Roughly, because you just need to add one gradient step term, but yeah. Again, I'm trying to advocate not liking the term optimum. You can plug anything you want in here, for instance, a ridge solution. Or for this problem, another way to do it is that you plug in the population optimum. So you're running gradient descent on a finite training set. There are two optima to consider, the optimum over the training set and the optimum over the distribution. The optimum over the training set might be trash that's uncorrelated with the population solution. You want the population solution. Could be, yeah, could be. No, there's a 2 here. Oh, okay, sure, yeah. But when I said this sandwiching, I was careful to write a bunch of inequalities. So
you're saying like gradients are always fine.
well, it won't, right? Because in general, it won't. It'll never actually equal. But okay, look, I'm trying to be very careful because in general, we don't even have optima. Minimize e to the x. So that's why I'm being very pedantic. But what I'm saying is you can get as close as you want and still satisfy this.
Yeah, maybe I'll just ask you offline.
Okay, yeah, I don't understand why I'm not understanding, but okay. Yeah?
So I just want to better understand the point of this setup. The point here is you basically say, okay, the usual way we analyze gradient descent is we compare the objective values that we got from the procedure with the optimum of the problem. But what you're saying here is that for the statistical learning style like problems where gradient descent arises in the first place, we don't want to find the optimum because you might have issues such as, for instance, the optimum has bad test loss because the optimum involves only the training data and not the test data. And so to do that, we want to generalize the original analysis so that instead of comparing how well we did with the optimum, we can compare we did with some other point, such as, for instance, whatever minimizes the test optimum, which is completely non-computable, but you can still think about it theoretically. And that's how I should think about the W bar.
Yeah.
Okay. And so what I want to understand then is what's the significance of like the norm condition? Because that just says like how far away from our initialization the 2 points are.
Yeah.
Like the sort of surrogate optimum or something like this. As the norm condition saying that whatever point we found is going to be a similar distance away from where we started. Like is that how it should be?
Yeah, let me show you another version of this. Yeah, I apologize. I realize I realize now that no one understands what I'm saying. Which is not the intent. So let me give another case. So let's go back to considering what I'll call WK, or I'll call this VK. No, I don't want to use that. Okay, W bar K. And this will be the ordinary least squares solution, but I truncate it. Sorry. Okay, so I'm back in least squares, and I'm truncating the ordinary least squares solution. Ordinary least squares solution is the pseudo inverse. In other words, this thing, if I had put an R up here, but I'm truncated it for some K, so this thing will be less than R. Okay? So you might have a statistical problem where the covariance craps out because you don't have many examples. And so you don't want to estimate the whole covariance matrix. You don't want to invert the whole covariance matrix. You're going to have small eigenvalues. What I'm saying is that if I initialize at W0 is equal to 0, then I'm going to be able to get a WT, which is similar in least squares laws to this truncated solution, and the norm of WT is less to 2 times the norm of WK. And the a typical test error bound has the form with probability greater than or equal to 1 minus delta, the gap between f of WT and the expected value of FWT. So F here will be the training error, the least squares loss on a training set will look like, it'll scale with the norm that we have. So a standard bound, the norm would be for our comparator. If we don't have something like the norm condition, we can't write down the right-hand side. We can't say anything about the right-hand side. But now I'm able to do this. And in particular, WK might be way, way smaller than the ordinary least squares solution. So let me say a standard alternative, you can run your standard optimization solver and your standard theorem, you can get that you converge to the ordinary least squares solution, but then you pay the statistical error of the ordinary least squares solution. And here I'm paying the statistical error of a much smaller solution. So that's the significance of the norm condition. Did that answer anyone's question? It's not an exclusive, yeah, it's not exclusive. The inequality, it does, yeah. Well, I mean, I'll prove it. I'm going to prove all of this for you, but.
Kind of like saying you're either optimal or you're like a small ball around your circle.
Yeah. Yeah, and like I said, for instance, for this high dimensional stats paper, the way the proof works is to use this with the estimator, which is that this is close. This is, you pick the iterate such that this, the first point where this holds, you have this too, and then you grind a bunch of concentration inequalities, a bunch of high-powered concentration inequalities, and you can get this thing. Yeah?
The W bar is like principal component analysis of the original data.
If you wish, yeah. Yeah, I'm using a lot of terms interchangeably. Okay. Okay, so what I'll do now is, and yeah, I apologize, like if it seems like I'm irritated that I'm not explaining this well, it's definitely irritation at myself and not at, it is 100% irritation at myself because this is something I'm very familiar with, so I shouldn't have trouble explaining it. So yeah, for all of you that feel unsatisfied, I definitely am blaming myself. And feel free to come up afterwards and explain what seemed weird about what I said. Let me prove this. So my plan now is to prove this and then give some remarks to close. And the remarks will include why I'm emphasizing this and also how to handle a bunch of deep learning cases using this as a lemma. Okay, so the proof is actually there was, I apologize, there was one remark I skipped and I want to say it because it'll demystify the proof a bit. For those of you that know the proof, I hope it still demystifies the proof. So the point I want to emphasize throughout this lecture is that the job of gradient descent really is not to optimize the objective function. It's really to balance the objective function and the norm. So I just want to remind everybody that another way of writing gradient descent is that in order to produce the next iterate, you minimize. So you minimize the linearization of the function plus a norm constraint. Okay, so this is another way of writing what gradient descent does. And I'm just trying to highlight that gradient descent was always trying to minimize norms. The job of gradient descent is not to minimize a function, it's to do both. So the way the proof works, you're supposed to look at a potential function, which is you look at a potential function which is given by norms, not by function values. So I'm just trying to make it clear why the proof is natural. Gradient descent is all about balancing function values and norms. And so the potential function we use to gradient descent, analysis gradient descent, is also about norms. Okay. Okay, so I'm going to look at the change in potential of this. And by the way, if you want to do the gradient flow proof, it's the same. You look at ddt of this quantity. And then you use fundamental theorem of calculus. So the same proof goes through for gradient flow. Okay, so if I expand the square, and let me just point out that this thing is ws minus eta grad fw. So if I plug this in and expand the square, I have one term that cancels this one. Then I also have this term, and then I have this term. Oh, excellent. I did not erase this. Okay, and now I'll use two inequalities. And another reason I like this proof is that it's going to use, well, it's going to use smoothness twice and convexity once. There is a way to make it use each once, but it's another story. So I'll use convexity once. And then I'm going to use smoothness here. So another way to look at this inequality is I put this on the left-hand side. Eta over 2 grad f squared is fw minus f next iterate. And I exactly have an n eta over 2 right here. So I have eta times fws minus fws plus 1. So I left out some subscripts. Okay. Sorry, I left out lots of subscripts. Okay. So smoothness, convexity. So then these two terms cancel. And actually, another consequence of this is that the iterate sequence has decreasing function values. So I'm actually going to use smoothness a second time, which, as everybody knows, is a crime, but that's my second crime today. Third, I think. So I get this. Okay. And then if you apply 1 over 2t eta, wait, did I already do the, oh, I already did the 1/2. Okay. If you apply this summation, this normalized, this average to both sides, then it implies this inequality. And now let me show you how to do the second one. And I have succeeded in killing this marker somehow. It was definitely not the Bruno. Bruno has like very gentle, precise handwriting, but I've like destroyed this thing. Okay, so to prove the other one, then I just do kind of the stupidest thing you could possibly do, which oddly works out very often. So if I look at wt minus w0 and call this whatever you want, call it expanding the square, call it AMGM, call it squared triangle inequality. I don't know what to call it anymore, but you get this. Okay, so again, the way I got this is I added and subtracted W bar on the inside. I expanded the square and did whatever you want to call it to get it. I don't know what to call it anymore. Uh, and then we can apply the theorem to. So if I apply the theorem, if I apply the star, so if I apply star to this, then I get 1 over 2 T eta W bar minus W0 plus FW bar minus FWT. And the point is that if this, if this is, sorry, if this is greater, then we have this inequality. So you look at the two cases in that way. All right. I have to explain a joke. So the way I test LLMs, every time a new LLM comes out, I ask it what its favorite proof of Cauchy-Schwarz and AMGM are. So I have like an infinite number of AMGM Cauchy-Schwarz proofs in my head, and they're all the same now. So whenever I look at any inequality, I'm like, that's AMGM Cauchy-Schwarz Jensen, and I just don't even know. I'm like totally confused now. So it's yeah, they've gotten really good at it actually. You can actually argue with the new ones about like what their favorite is. It's pretty cool. Okay, so any questions about the proof? So the proof, convexity, smoothness once, smoothness twice. You get this, you apply this to both sides to telescope this term. If it had just been gradient flow, we would have just done DDT, gotten this term, integrated both sides, same result. And then this is just algebra basically, and then you interpret the final statement and you get this. In other words, if this quantity was larger than this quantity, we haven't optimized a lot yet, then that would mean that we can just upper bound this by 0. So we have this less than or equal to this, and then we cancel a bunch of terms and square root both sides, and the 4 becomes a 2, and we get this. Okay, so any questions about the proof? Yeah, and I apologize that I did not explain it very well. I should say that even though this might look very modest, people in the audience that clearly a lot of you know the standard proofs, you might just be saying, why is such a big deal about this term? So the number of things that I've seen over the years that are a consequence of just using this is pretty remarkable. There are lots of statistical guarantees where you had to do a complicated estimator or something, and it turns out gradient descent satisfied it, and you could just use this. So that's why I'm highlighting this. It's pretty robust. Okay. So if there are no questions, I will treat the rest of the time as remarks, but I will cover a few deep cases. So any questions while I erase? And I'll try to explain things better, I guess. My best. All right. Okay, I just want to make one remark about the stochastic case, because there's a very nice variant of this that you can get in the stochastic case. I was actually kind of surprised by how short it is to prove this. And so stochastic case, and another nice thing about the stochastic case is that I'm just going to define the stochastic case as being this. And inside the proof, I'm going to compare this to the gradient of what we wanted, but I'm never going to use any, there's not going to be any statistics in the theorem. There's no probability. So this is the iteration. And inside the proof, I'm going to have the difference of these two. I'm never going to claim that that difference is whatever, zero in conditional expectation or something. I'm just going to write this, and we don't have to reason about probability. So the analog you get, oh, and then we need, and I'm also going to need an extra term alpha, and my step size is less than this. And I should say that I just found this variant of the proof in Sebastian Bubeck's optimization notes. So the version he has is the one without the arbitrary comparators for using the optimum. But I'm giving the version with. So everything looks the same. So now, okay, everything is looking the same. Oh, and I need this to be smooth. But I have two extra terms. So the first one is this gradient error, which of course this term we can only control if we have a good, some sort of statistical property. Well, sorry, we can control it on a lot of settings, but one is if we satisfy sort of martingale structure or something. And then the other term is this pretty interesting variance term. Sorry, I might need a 2. Okay, so I like this a lot because I've used nothing about probability here. This is just a GS. This is a grad FWS. I just add and subtract in the proof, apply convexity. So this is convex and smooth. I apply convexity and smooth. I just add and subtract between these two in an appropriate place. No probability used anywhere in this proof. So it's the same thing as before, plus this thing. You can interpret this as a variance, but again, I haven't said anything about probability. So this for me is my favorite way of, right now, it's my favorite thing down the edge here. So you get morally the same thing. I'll also point out that in order to control this martingale, you have to control this norm. But guess what? You've already controlled it. So you don't need to project, is what I'm saying. Okay, so that's one remark I wanted to share. Okay, let me tell you another remark, which is about the NTK. So in deep learning theory, we only really developed one general tool, which was able to get us very general and short. Okay, this is a loaded statement. So okay, we have two general tools. I'll just be polite. One is the NTK and the other one is the mean field analysis. The NTK is kind of the opposite of feature learning. So no feature learning, and I'll explain that. However, my personal taste, it's very nice because it's very easy to do this analysis and it's very quick to get sort of a baseline that you can compare against. So let me be a little bit more explicit. So the NTK sort of philosophy is that we look at situations. So we look at, for gradient descent, we'll look at WT such that the gradient, or sorry, the function values of my iterate are well approximated by those of the Taylor expansion. Okay, so I need this. I'll define this to be the NTK error to be small. Okay. So there's like an infinite number of ways to define the NTK. And there's an infinite number of weird things people say about the NTK. For my purposes for this remark, I'm calling iterates that satisfy the NTK being those where this, a first order Taylor expansion is small. Okay, why does this help us? It's actually very easy. So the reason that this helps us is that when I have the gradient of a loss of some iterates inside the proof I just showed you. And I do chain rule once. So I get derivative of the loss on the ith example. So I'm just leaving out all the terms. And then by chain rule, I have the gradient at the iteration. Okay. What the NTK philosophy lets you do is it lets you swap in the function values here. So because of that Taylor error, what you can do inside of proofs is you can just swap in f of w bar, sorry, fi. I'm calling it fi, which is the prediction on example I. You can swap in this with something related to this Taylor error, and you can control this term. And then you can push through the entire proof I just showed you, and you accumulate one more error term down here. Okay, and this results in an extremely short proof. You can prove, for instance, a gradient descent in this regime in just like 2 pages. It's insanely short and very transparent. And let me give you an example. So example, so the 2 XOR that I told you about yesterday, that was this thing where if we could learn features, we would converge to these 4, all the ReLUs would move in these 4 directions. Sorry, at most, initially they all move, but then eventually just one moves in all the 4 directions. So for this one, I mentioned that sort of the gold standard for whether you learn features or not is to look at the sample complexity. So there's a lower bound. This lower bound was actually proved by, there's this paper by, I'm actually having trouble remembering all the authors. I think these are the authors. I mainly remember Colin Way. So there's a lower bound which says that the NTK test error on this problem is d squared over epsilon. So to get epsilon test error on this problem, you need d squared, you need this many samples. So there's this lower bound. And if you grind through this proof, so if you grind through this proof, where you have your statistical error and you have your variance term and you have your NTK error term, okay? And to be clear, to control your statistical error, like I said, you need this term. So you grind through this, and then you'll get that the NTK number of samples is less than or equal to d squared over epsilon. So you get it tight with the lower bound. And I actually don't know any way to prove that other than using this technology. So in particular, if you try to use, lots of other general techniques, it's actually pretty hard to get this d squared over epsilon. So it's non-trivial in the sense that many papers that have upper bounds for this problem, their upper bound is much worse than this. Okay, so that's comment number 1 about the NTK. The only other thing I want to say about the NTK is just a bit of the sort of NTK mantra. So I feel like I'm contractually obligated to say this, but so the NTK error that I called this epsilon NTK, this Taylor error, so it usually scales with 1 over the width of the network. There are many cases where this is easy to show, but what you can get as an implication is that you can sort of make this inequality easier to satisfy and extend this phase. So I was planning to actually go through that today, but I spent too much time on the earlier stuff. So yeah, if you're curious about this, I can just explain it later. But again, part of the reason I'm including this remark at all, even in this abbreviated form, is just to say that the form of the bound and this Taylor error, they plug directly into inequalities of this type. So you're still just using this directly. Okay, that's comment number one. And now I want to tell you, before we stop, about the feature learning case that I started to mention last time. So any questions about anything I just said right there? I mean, I went very fast. Yeah?
Like have a kernel which tries to be the quadratic function. Don't we just expect this?
Well, first of all, this was for the cross entropy, so it wasn't. It's not direct from covariance estimation. I mean, it is true that it's definitely the case that if you just took d-squared samples and just it does feel like there are. Okay, how do I put it? If your goal was just to solve the problem with d-squared samples, it's certainly trivial. It is definitely the case that the covariance concentrates very rapidly, and you can read off the solution. Actually, I was going to say something about that right now, too. In fact, D samples is enough to read something very nice from the covariance matrix. The point here is that that's what gradient descent needs, and the proof is really short. So there's a lot of NTK optimization papers that are like 80 pages long and hard to read. This is really like a 2-pager. Oh, and I should say that it's a 2-pager with a general methodology, and then you just compute like one kernel term with matrix concentration, and then you get the d-squared. So maybe to connect it to your comment, yeah, your comment would basically say, one way I can combine what you said with what I said is that there's a kernel term here, which is what you said, which is d-squared. And I also confirmed that if your goal was just to solve this problem, then it's definitely a short proof to do it with just d or d-squared. Okay. But yeah, you're right, I should have said that before. Yeah, it's good to include that baseline. Okay, so let me make a remark on feature learning. So as I've mentioned, we've sort of entered the analysis of LLMs without an adequate set of tools. The analyses of gradient descent on transformers that exist so far, they basically remove the MLP, they linearize everything. They do not have a toolbox from the deep learning theory community to use. Okay, so the situation's not great. We don't have many tools, but I will tell you just quickly how some of the proofs work, what I can do in 4 minutes, and yeah, then we'll stop. So for the 2 XOR, there were 2 problems. So I mentioned that you have to learn these 4 values. By drawing this problem in 2 dimensions, I'm actually obscuring sort of the key thing you really have to do, which is effectively what Bruno was referring to, which is you have to find out where the action in the problem is. You have to isolate. This is a problem in D dimensions. Let me just remind everybody that this was X sampled according to uniform on the corners of the hypercube. But the labels were just the first 2 coordinates. So effectively what the problem really boils down to, which is what he was saying by the covariance estimation, is you just need enough samples so that you can look at the covariance and see, or look at something and see that you only really should care about the first 2 dimensions. All the other dimensions kind of cancel. You really only want to look at the first 2. So I'll make 2 remarks in regards to that. So the first is that I'll just say vaguely, so many papers, and one of course, many papers use a two-stage analysis or multi-stage in the case of some of these, for those of you that are familiar with these staircase papers, or they use a multi-stage analysis where phase 1 does 1 step of GD, one GD step on order D fresh data, and reads off a good subspace. So this is exactly what Bruno was saying. And I know it might seem like I'm just writing what he said on the board, but it was actually one of the next remarks I wanted to include. So this is a key ingredient in a lot of the proofs. They have one stage where if you just look at the gradient, if you look at the gradient of this one at initialization, if it's at initialization, you have random weights and then you have this randomness. There's a lot of cancellation and this subspace just kicks out even with just d log d samples. It's very clear. So I said order d, I should really say d log d. And then phase 2 freezes some weights and learns, I'll say convexly on top of that. Okay. So for instance, if you want to get the d over epsilon, it is enough to do this procedure. So if it is enough to beat the d over d squared of epsilon that you get here with upper and lower bound by just doing one step of gradient descent on both layers, analyzing just staring at the gradient. If it was the least squares loss, we'd immediately just have a covariance, but just for cross interval, you also get something kind of like the covariance. You can just read off the effective subspace from it with d log d samples, and then you freeze that first layer. So this is an analysis technique. It is not the algorithm. I'll say to my knowledge, the only paper that does not do this, the only paper that truly analyzes gradient descent, so it does not do the two-phase thing, is the Margalit-Glasgow paper I mentioned. So Margalit-Glasgow is the only one that does not freeze, but it's very, very hard to not freeze. It's just like insanely difficult. Actually, I'm out of time. So the only other comment I was going to tell you was this is one ingredient, is that you have to do this phasing. I mentioned last time this F1 versus F2 thing. I was going to explain it, but we're out of time. Maybe I'll say it next time. But I didn't actually explain how the F1 versus F2 arises. I messed up time. But let's stop there.